Okay, so hello everyone. So today, what if I'm telling that to you that you could hack anyone Bitcoin's wallet in the future, or that you could just teleport information through space and time? This is something that is possible when we are shifting the paradigm from classic computing, something that we all know today, to quantum computing. So the purpose of today would be to demystify a bit the magic that you would see around it, because some of the reality behind it seems like magic. So it is intended for people who don't know absolutely nothing about the subject. So that's perfectly fine if you are not familiar with quantum computing. The purpose is to explain a bit the basics and the intuition behind it. And if you're already familiar with the subject, I will focus on the cybersecurity implication in the future, but already today. So first, before that, I will just present myself. So my name is Descamps. I have a classic background in IT. So I just have a background in computer science, very classic background that's important to tell here. I'm an ethical hacker, so specialized in penetration testing and red teaming. I'm a consultant at PwC Belgium. I'm a colleague of Pedro, who did the talk about rack system this morning. And it is an important precision that I am not an expert in quantum computing and definitely not in quantum mechanics, because I'm not a physicist. But I got an interest in that field 1 year ago when I participated to the DEF CON, and I was very active in the Quantum Village, where I secured the third place at the CTF there. So this was a bit the start of the spark of interest I got in quantum computing. So I think for you ethical hackers here, it will be interesting to have the point of view of someone with a classic backgrounds. How can we demystify this subject that seems a bit complex and difficult when we look at that from an external point of view? So we'll first define what is quantum computing and quantum mechanics, because it's based on that. Then we'll see how we do quantum mechanics, quantum computing with famous algorithms. I'm sure you've heard about the Shor's algorithm. We'll see how it works here. We'll talk about quantum key distribution. This is one of the strengths that is brought by quantum computing. And then we'll just try to make a conclusion. Today, are we doomed when we have a powerful quantum computer that is powerful enough to do interesting things? And then some resources on how you can learn about this subject, because it's not always easy to find your way around it. So first, let's define what is quantum computing. And first, let's define the difference between classic physics and quantum mechanics. So you all know classic physics. This is a way to describe reality, if we summarize it. But here, the classic physics is actually a nice approximation of the reality. This is a nice model when you are analyzing on a microscopic level, so what you can see from the bare eyes here. But actually, when you look on the microscopic level, so on the atomic level, classic physics, this model is not enough. You cannot explain what is happening on an atomic level. So for that, you need quantum mechanics. And actually, when you look at the ways, that's the graph that I try to make here, quantum mechanics actually is the description of the entire reality that surrounds us. You just have classic physics as, let's say, an approximation of what is happening. But if you look closely at everything, everything is quantum. So we just need to introduce new concepts for quantum mechanics that we'll exploit in quantum computing. It is superposition, decoherence, and entanglement. So first, superposition. I'm sure you've seen this image a few times already, the Schrödinger's cat. This is an experiment where you put a cat in a box with some poison. You close the box, and as soon as you don't open the box, you consider the cat both alive and dead. This is called superposition in quantum mechanics, meaning that as long as you don't look at an electron of an atom, for example, to take that as a quantum unit, the electron could be a bit anywhere in the, it could be on the top, could be on the bottom. This is a probability, but you are not certain about it. until you measure it. When you measure a quantum unit, you force the state to be 1 or 0, like in a classic state. And then you lose a bit the quantum strength of it, because once you measure a quantum unit, it becomes a classic unit. So it's not quantum anymore. It would be to take the Schrödinger's cat again, it would be the result of opening the box. You will see that the cat is dead or alive. And then you have the last one, entanglement. That's maybe the most difficult concept to understand. This describes the fact that two quantum units could be linked together through space and time, meaning that you could have a qubit here on the scene and a qubit at the rear there. They could be linked together, although you have a space between them. But that could also be on different planets or galaxies, or even at a different time. So meaning that if you apply an operation on one of the entangled qubits, the other one will be affected. This is so weird to understand that even Einstein had doubt about it and didn't believe that and thought that there were some hidden variables. And it was demonstrated later that, no, entanglement is a real concept. So what do you need to understand quantum computing? You do not need to be a physicist. So this is what reassures me when I discover the subject. The only thing you need, let's say, is mathematical concepts. So if you're familiar with linear algebra and complex numbers, and that you're not scared of that, you just build on these two concepts and you can actually explain everything in quantum computing, so you're able to build algorithms yourself. So the last concept to define in quantum computing is the qubit. That's the fundamental element about quantum computing, because in classic computers, we have a bit, could be 0 or 1, very simple. In quantum computers, we have qubits. They could be 0, 1, or something between the two with a certain probability. Here we could describe some classical state here. You have the 0, so that's the way that we express the qubits in mathematics using linear algebra here. So just noting you the notation here, this is not really important to take into account here, just to demonstrate that everything that I'm about to tell is logic and not coming from just a weird magic or something. So you have the 0 state, 1 state, really easy, really comparable to classic states, and then you have the plus and minus state. It's 50-50% probability that it will be 0 or 1. The difference between plus and minus is a phase. This is not something that we will see today because it's not interesting for an introduction. So please bear with me, because that's in the next 5 minutes, that may be the most boring part or the most difficult part for the people who don't really like mathematics. But this is, again, necessary so that you understand how actually we are doing operation on a quantum computer. You know that on a classic computer, if you look at the low level, it's only operations that are expressed as gates. So you have bits, and then you apply gates on this, like OR, AND, XOR, etc. This is the same logic with quantum computing. We are building circuits using gates. The only thing is that we introduce new gates thanks to the property of qubits. So let's take an example here, a simple circuit. We have two qubits, X and Y, and we have this circuit. The purpose is that if the control qubit, so that's the top one, that's Y, if it's equal to 1, then we apply the NOT gate on the qubit X. This is the target qubit. In details, how do we express that? I will not get into the detail of how we have this matrix here, but basically, if you just take this matrix and you multiply what you saw on the previous slide, you will end up on the right result. So the H here, it's a famous gate in quantum computing. This is called the Hadamard gate. You see that it's a combination, a product of identity and Hadamard, because we have two qubits. Identity does nothing to the first qubit, X, because there is nothing. And then we apply the second matrix there, that's Hadamard gate, that we apply to Y. And then the second one, that's the conditional NOT, C NOT, meaning that it will apply NOT on the X qubit only if the Y qubit is equal to 1. Let's take an example here. Let's say that we have the two qubits that's equal to 0. By the way, maybe you understood that you see this weird notation here with a bar, 0, and then a kind of a bracket. That's called the direct notation, and that's kind of handy here because you would see that if we would just use the full matrix, it would take too much space. So it's just a way to express a matrix in a short way. It's called the Kedra or direct notation here. So when we are at pi 0 on the circuit, nothing happens, so we have 0, 0. This is logic. We have our 2 qubits. They are initiated to 0, 0. Then we apply the Hadamard gate to the y qubits. Applying Hadamard gate on a qubit that is equal to 0 will result in the plus state, so the 50-50% change, so it's now in a superposition state, like we saw. The right part of the expression, this is just another way to express the 0 plus, because it will be necessary to understand the last part of the circuit. We can just express that in another way. And then we have pi 2. After, between pi 1 and pi 2, we apply the C0. So meaning that for the first pair that you see on the right of the expression, you have 0, 0, meaning that the y is equal to 0, so we don't do anything to x, 0 remains 0. For the second one, we have a 1 for the control qubit, meaning that we apply a NOT to the x qubit. So 0 become 1. So 0, 1 become 1, 1. And this is not a random circuit that I brought to you. This is called a Bell state. I hope you're still following or that you are not bored already. Believe me, this is the only complicated things that I will show you now, but it's just to build on that and show you how the interesting algorithm for cybersecurity work actually. And so the last circuit that we will see is the circuit for quantum teleportation. So teleportation here doesn't mean that we'll just teleport matter from a place A to a place B. This is not possible. Even if you're changing the model of reality, this is not something that you can achieve. It's not true teleportation in a fictional sense. Here we mean that we'll teleport qubits from one place to another place. How do we do that using that circuit? So you see above you have the psi qubit, and the objective is to transfer the psi qubit to another party. So you have A and B, Alice and Bob. Alice wants to communicate the qubit to Bob. Here we're only using classical channel, meaning that Alice and Bob will communicate with classic bits, but that's the only thing that they will use. The condition for that, you see that on the left, would be to have Alice and Bob sharing an E-bit. What is an E-bit? It's just 2 entangled qubits that Alice and Bob share. This is a great example of why entanglement can be used to perform such weird operation. If you see that from the exterior, you see that we call that teleportation, but actually it's nothing complicated if you accept the concept of entanglement. So we do a series of operations there. You see that you have the conditional NOT gate, like we saw, the Hadamard gate, and then you have this white square there. This means that we measure the qubits, but you remember that when actually, when we measure the qubits, we introduce decoherence, because a qubit is really fragile. That's a unit that is really fragile and really likely to be disturbed by anything, any physical reality, a phenomenon that you can see. So temperature, static electricity, electromagnetic field, things like that. So here, actually, we take measurements, meaning that the double line that you see on the right, we are using, after the measurement of the qubit, we are not dealing with classic bits. And then B, receive these classic bits and apply a conditional X and Z gate. This is simply this gate here. And then apply, if the first bit is 1, we apply X. If the second bit is 1, we also apply Z. And then, magically, we have the psi qubit that is teleported from A to B. And they could be at any distance, as long as A and B can communicate together through a classic channel. OK, so that was the difficult part. We are done with mathematics now. So now we are coming to the interesting part for cybersecurity, because you have a lot of application for quantum computing. Because we are relying now on quantum mechanics, it means that we can fully emulate reality at the opposite of just 0 and 1 that we have in a classic computer. The most simple and greatest example for that is just atom and molecule simulation. On a classic computer, each time you add a molecule to your simulation, it will exponentially grow the complexity. On a quantum computer, this is not the case, because with quantum computing, you can just emulate this as it is in reality. So actually, could, for example, for the pharmaceutical and chemistry industry, this could lead to breakthrough, to discover new medicine, things like that. So this is one of the numerous applications. But here we are not focusing on that today. We're focusing on the cybersecurity implication. What is the implication for us ethical hackers? The first interesting algorithm to see is Grover's algorithm. This is an algorithm that can search for a precise result in an unsorted database. And when we are running Grover's algorithm on a quantum computer, we have a quadratic speed up on the complexity here, meaning that it could be a threat for brute force attack on hashing and symmetric keys here. It could be, but it will only weaken a bit the hash security here. So you see that normally you would brute force everything with a classic computer. If you have a quadratic speed on that with a quantum computer, actually you will just reduce a bit the real security level of your hash size. But you just need to be careful in that case to increase the size of your hash. Same for AES, for example, famous symmetric encryption here to try to brute force the key. Here we just discovered that if we have access to Grover's algorithm on a quantum computer, AES key size of 128 bits will not be secure anymore. But here it's really simple. In both cases, you just need to increase the size, and then it's solved. You're immune to quantum computing threats. But that's the good news. The bad news is Shor's algorithm. That's really the star here of all algorithms on quantum computing, because this is the real threat here. Because Shor's algorithm can solve a famous problem that is just encompassed, embedded in the asymmetric encryption today. Basically, this is difficult to... I will not show you the mathematics for Shor's algorithm, because myself I couldn't explain fully, because it's way more complex than the simple example that we saw. But to give you an intuition, normally with a classic computer, so to break asymmetric encryption, so RSA, Diffie-Hellman, you will try to take the big number that you have there and try to find the prime numbers that were used to calculate that big number. That's the problem you want to solve. With a classic computer, if you have the number that is big enough, the complexity is too high. Even if you have a lot of computational power, not possible if the key size is big enough. But with quantum computers, you can do that. You can use the parallelism power of quantum computing, meaning that you can consider here, the intuition is that you can consider all the prime numbers candidate to be the one to solve, to decompose the big number, as a probability. And you can consider all this probability at once. And so what you need is apply gate operation there until you see this prime numbers probability emerge. And so at the end, you just select the qubits that have the highest probability. This is really a very, very simplified explanation. It's just to give you the intuition behind and why it is so powerful. And that you could increase your RSA key size tremendously. This will not change the fact that quantum computing will be a real threat to that. So if you're not convinced, because you don't know RSA, Diffie-Hellman, so this is something that is a bit mysterious to you, this is everywhere, actually. Asymmetric encryption is everywhere. The TLS certificate that you have on website to ensure that they are secure, the IPsec protocol used for VPN, BitLocker on your Windows, the whole payment industry with credit cards and payment, etc., the current TPM, some messaging apps, all of these, if you have a quantum computer today that is powerful enough, you can break all of that. That's a problem in the future, of course, because we don't have a powerful quantum computer today. But it is still a threat today and yesterday. Because what you could do, actually, as a hacker, is to harvest this communication today, you store them, and then you wait, you have your quantum computer, you decrypt them. So you just wait 10, 20, 30 years, and then you can decrypt conversation. This is a threat for high confidential conversation, like government communications, things like that. So this is why this is a problem to tackle, not tomorrow, but today, and even yesterday, I would say. This is also a threat to cryptocurrencies, because Bitcoin, Ethereum are also based on this problem that can be broken by Shor's algorithm. So with all of that, what does that mean? Does that mean that you should just panic, cry, sell your cryptocurrencies, and switch maybe to QRL? This is a cryptocurrency that is resilient against quantum threats. Well, I will answer to that question. But first, I will just make a small detour and explain a bit one of the big strengths that quantum computing is bringing to us. This is quantum key distribution. So key distribution is a known problem. You want to establish a secure communication, but for that you need to establish a key on a public channel. How do you do that? Well, if you cannot do that with Diffie-Hellman anymore, maybe QKD, quantum key distribution, would be the way. The intuition behind quantum key distribution is that you will communicate from Alice and Bob with qubits, so with quantum communication. And you see that there is a theorem that is called the no-cloning theorem, and it's using actually the concept of decoherence. If you have someone eavesdropping the conversation, Eve, in between, actually you will introduce decoherence because you cannot look at qubits without introducing decoherence. So as soon as someone looks into that, you are sure, Alice and Bob are sure that someone looked at the conversation and will just stop creating the key. So quantum key distribution, in the principle, it's not protected by a mathematical problem. It's protected by physics itself, by reality. So to break quantum key distribution, you need to break reality, which is quite difficult to do. Here you have a preview. You see on the left the BARP receiver from the DARPANET, the first quantum key distribution network that was built that looks like some stuff like this. On the left, you see names of protocols that we use for quantum key distribution. And on the right, you see the future first quantum key distribution European network that will be deployed by European Space Agency. So communication concretely is done through space, with satellite, but also with optical fibers or supraconducting circuits. So QKD is perfect, right? The two downsides here. One downside that today it's still costly, costs millions if you want to build such a network. So the stakes must be high for that, but that's a solution that is at hand if you have the means to do that. And the second problem is that, yeah, it is perfect as long as you perfectly implement it. To give you an image, maybe you know that game Connect 4. Connect 4, you know that it's a game that is solved, meaning that if you are the first player to play, you are ensured to win, as long as you play perfectly, which is not really a characteristic that is very human. So QKD is really vulnerable to side-channel attacks. You really need to see how it is implemented, and that's where you will find all the vulnerabilities. So it's still not perfect. And to end up on QKD, I will just show you, okay, concretely, how do we do that? By just presenting the first algorithm that was built for QKD in 84, actually. So it's called BB84 here. So the principle is that we have Alice and Bob, once again. Alice wants to send bits here. That's the bits that will be used to construct the key between Alice and Bob's. Alice needs to choose bases to do the measurement to create the qubits. So Alice has the choice of X and Z gate for the measurement to create the qubits here. So she will arbitrarily choose X and Z. This is not important. And then according to if it's 0, X, 1, or Z, you have the combination on the above. There you will obtain certain quantum states. These states, you will send that to quantum communication to Bob, and Bob will measure them, but Bob doesn't know what the bases are, so Bob will just randomly choose X or Z, because that's the best that he can do. And then using X or Z, he will obtain a certain measurement, and then he can derivate the bits. Once everything is done, Alice and Bob can publicly share what was the base that they use for each of the bits, and they just keep the bits that where the states corresponded. So if it was an X in both sides or Z in both sides, they would keep the bits, and that will form the key. So pretty simple, right? So what if we just intercept what is between? What if Eve tried to guess the bases and try to measure the qubits? Well, Eve will do the same as Bob. She will just choose random states and do measurement and then send what she just measured to Bob. And Bob will do exactly the same here. But by looking at the bits, when comparing all the states, Bob and Alice will realize that actually the key that they form together does not correspond. It's not something they could agree on because the key does not correspond to the conversation that they want to do. Actually, some of the bits were actually off. So it's impossible for them to establish a key in that setup. And that's just an illustration of if anyone is looking at quantum conversation, you just introduce decoherence, you're ensured that something went wrong. It's also possible that you had other disturbance there, but for security reason, Alice and Bob will choose to discard the key and restart. So now the interesting question maybe for you today, is it soon Judgment Day? So does it mean that when we have a quantum computer that can break RSA is in the end of the world? Do we need to fight quantum computers with quantum computers? Do we need to implement QKD everywhere? Well, the first question is like, when will this happen? Because everything that I'm telling now, it seems a bit theoretical in the future. Can we predict when will that happen? When can we have this shift of paradigm? This is more or less the number of qubits that we have at disposal right now. So one important element to run certain algorithms, so Shor's algorithm, that's the most important one, we need 20 million physical qubits. For now, the most powerful computer has maybe 5,000 physical qubits, something like that, more or less. And from that, we try to derive kind of a Moore's law, so that's the same, similarly to what we have with classic computing, trying to see, okay, when actually do we have enough qubits to actually run Shor's algorithm on a key size of RSA that is big enough. 20 million. So you see that if we do projections here, we are still safe for maybe, I don't know, 20 years, 40 years, 30 years, something like that. Well, that's one element to have qubits. A second element is breakthrough in algorithm research. This was published a few weeks ago. This is a Google researcher who demonstrated recently that he could break actually an RSA key, so of 2048 bits, with just less than 1 million qubits. So we have 20 million, and now we just need 1 million. So meaning that the deadline is just even closer now. You also have a third element. That's the capacity to use these qubits in a smart way. Because like I said, these qubits are very fragile. Any turbulence, any disturbance out there of reality, whatever, they could be useless. Because as soon as you disturb them, they become classic bits, and then we are not interested in that anymore. So the logic here that you see on the top here would be to group them together and to make kind of a error correction algorithm. So you take 1,000 qubits together, and then you have one logical qubit that is immune to error, and that's how you form your qubits that you can deal with. You have a company, a French company here called Alice and Bob, doing innovation around that, for example, around these error correction processes. They have an innovation called cat qubits, and actually with cat qubits, they do not need 1,000 physical qubits to have one logical one, but only 30. So by doing this kind of innovation, we're also closer and closer to run Shor's algorithm. They published a really nice white paper recently, so I encourage you to see what they are doing if you're interested in the hardware part here, because they really explain everything with a lot of details. And if you're looking at their recent roadmap, they predict a quantum computer to be powerful enough by 2030, which is not far at all. So does it mean that we need to wait 2030 and just, maybe pray, something like that, and just wait so that we have a quantum computer? Well, no. You have what we call post-quantum cryptography. Actually, this has no link with quantum computing. Post-quantum cryptography is just changing the cryptography algorithms that we have today so that they use another problem, not the prime decomposition problem, but another one. And this problem will be resilient against classic computers, of course, this is important, but also against quantum computing power. For that, one of the candidates that was selected by NIST is Crystal Kybers. It's using lattice encryption. And to explain you briefly the idea behind, you have a lattice here. All the points represent data here. And here you represent actually the private and the public key by these sets of vectors. So the red one here, the long one, will be a byte basis, what we call a byte basis here in lattice encryption. This will be the public key, and then you have a good basis. The intuition behind is that the problem you want to solve here is the closest vector problem. This is easy to do when you have a good basis. This is hard to do when you have a very bad basis. And so concretely, what you will do is with your public key, you will encrypt, you will choose something, you will choose a point on the lattice and then introduce some randomization so that it is really, really difficult to find back with a public key, but easy to do with a private key. So is it already implemented today in the solutions that we use nowadays? Yes and no. So let's take a few examples. This is on the left. You see this is an extract from Apple. You will see that here, for example, iMessage is already implementing PQC for like 2 years or something like that. The Signal protocol that is used by Signal, but also by Messenger, and I believe WhatsApp now, Instagram, etc., it's implementing PQC as well. For other more difficult subjects like Ethereum, for example, you don't have one guy behind Ethereum like Apple deciding for like a change of algorithm there. So, but in the roadmap of Ethereum, you will see that they consider quantum resistance and they want to make the switch as soon as possible. So no, do not sell your cryptocurrencies, at least not today, for that reason. You have other, it's important to look at that because you have a lot of solutions that are not considering PQC already. Some of them are already considering that for quite a while, so interesting to see. And if you're looking at the best guidelines that would be coming from NIST framework, you would see that they advise here, to summarize, to deprecate any current asymmetric algorithm that is using the prime number decomposition problem. They advise to deprecate that for 2030 and to disallow them for 2035. But you will see that this prediction is already maybe a bit optimistic given the result that we just saw today. So, okay, that was the conclusion about quantum computing. So now you, as ethical hackers, how can you learn about this subject and the cybersecurity that is linked to that? Well, first you have a few events and communities that are around that are really nice. So you had, for example, the France Quantum Conference. It took place just last week. You have the World of Quantum happening at this very moment in Munich. You have also other initiatives on an European level. You have the Quantum Village at the DEF CON, which is really the intersection between quantum and cybersecurity. So they really have nice project initiatives there. They organize a CTF every year, and I think they are the only one to organize a CTF around that so far. They also have the project to be present in more locations than just Las Vegas yearly. So definitely a community to follow there. You also have Hack the Box. Recently, they released a quantum track if you want to try some quantum-related challenges. So we're starting to see quantum integrated in CTFs for ethical hackers. If you want to learn about coding with quantum computing circuits algorithm, you have the Microsoft Quantum Katas. If you want to learn the Q# language that is specific to build quantum circuits. You have IBM has a ton of resources to learn about quantum computing on both high level and low level. So they maintain the Qiskit framework for Python. So actually by just using Python, you can simulate quantum circuits. And then you have a no-code alternative in a more interactive way. For example, Quantum Flytrap, where you can just design your circuits without using any code, actually. And you have tons of other alternatives. So actually, that was a bit, the purpose here was to introduce the concept, to see that, okay, it has dangers, but also wonders here. The fact that it is very, very important in terms of cybersecurity. I thought it was really important here at Le Hack for you to explain what it is if you are not aware of what quantum computing was and the link with cybersecurity and the need to take that into account in your roadmap towards your learning. So thank you for your attention.
Any question? En français ou en anglais? In French or in English?
So thank you for your talk. I have a question. So how we do measure the computing power of a quantum computer to say, for example, that this quantum computer is more powerful than this one? Is it based only on the number of qubits that the computer supports, or so there is other factors like underlying technology, etc.?
So, that's yeah, so what is the metrics to determine if a quantum computer is powerful enough, right?
Yes. Yes.
Yeah, so like I said, it could be the number of qubits, but it's a bit a simplification because it also depends on the number of gates, the operation that you can actually perform on a quantum computer. But basically, the nice metric for that is the Shor's algorithm, because if you have a quantum computer that can run Shor's algorithm, basically you can run anything else. So when we reach that ceiling, that's where we have what we call the quantum day. We really have the quantum advantage, and this will be the game changer for the quantum paradigm. Because when we reach that point, quantum computers become basically useful.
Yeah.
Là-haut, il y a quelqu'un qui a un micro, non? Parle.
J'y vais. Okay, I have a question about quantum key distribution. I was wondering about the prerequisites of implementing such technology. Is it possible to do it through a regular network, or does it need special infrastructure between both communicants?
Yeah, it depends on because it depends on the hardware that you're using. Because in communication, you could be using trapped ion, you could be using photons, you could use supraconducting circuits. Depending on the hardware, the requirement will be different. So optical fiber could be something that will be used with photons, for example, if I'm not mistaken. Basically, the vector of communication that you want to have is an empty one, so through space or something that is really clear of any disturbance.
Okay.
So that's something we could use today. We could build. Also, it is already in place in many governments and companies, actually.
Okay, thank you.
Okay, there is one on the left here. Please stand up.
Bonjour.
Bonjour.
Je peux poser la question en français, il me semble, c'est bon?
Oui.
Oui, pas de problème.
Actuellement, quand on doit chiffrer des données, un des paramètres pour le choix de l'algorithme, c'est est-ce qu'on a de l'accélération matérielle pour ça? Où en est l'industrie pour utiliser des algorithmes qui vont mieux résister à ce type d'attaque? Si tu sais.
Donc ici, l'algorithme de Shor, par exemple ou...
Par exemple, pour résister à ce type des algorithmes qui résisteraient à la résolution des nombres.
Ah oui, ok. Donc
une accélération dessus, matérielle, parce que c'est un des paramètres de choix quand on choisit un algorithme pour le chiffrement.
Ah, quand on choisit le PQC, tu veux dire peut-être. Donc quand on switch d'algorithme, donc pour se protéger, en fait, on va utiliser du PQC. Donc on va switcher, on va plus utiliser du RSA Diffie-Hellman, on va utiliser autre chose. Kyber Crystals, par exemple. Je ne sais pas si c'est ça ta question.
Ma question, c'était si tu avais des infos vis-à-vis de l'évolution du matériel là-dessus, par rapport à l'accélération matérielle. Par exemple, sur les processeurs Intel, on a des instructions d'accélération AES spécifiquement, qui permet d'économiser des cycles processeurs quand on fait ce genre de chiffrement.
Ok, et donc ce serait plutôt au niveau de l'hardware de quantum computing, alors ta question ici. Difficile pour moi de répondre. Il faudrait que quelqu'un d'Alice and Bob pour ça ou quelque chose comme ça ici, parce que je ne suis pas spécialisé en hardware. Maintenant, en fait, comme je disais, il y a plusieurs dimensions sur lesquelles on peut s'améliorer ici, parce que augmenter le nombre de qubits, oui, ce sera très bien. Pouvoir utiliser moins de qubits pour faire la même chose, c'est cool aussi. Maintenant, je pense que ta question serait plutôt par rapport au nombre d'opérations que l'on peut appliquer. Donc le nombre de gates en fait, que l'on peut appliquer dans un même ordinateur, c'est aussi un élément à prendre en compte. Et donc du coup, il y a aussi des innovations autour de ça.
Ok. J'ai peut-être mal posé ma question, ce n'était pas exactement par rapport à ça. C'était plus le côté protection que le côté attaque sur la partie matérielle.
Aujourd'hui, en fait, si jamais on a un ordinateur quantique qui est assez puissant, RSA, Diffie-Hellman, personne n'est protégé en fait aujourd'hui.
Tout à fait.
Voilà. Donc du coup, en fait, tout dépend du fait que les solutions, les protocoles qu'on utilise, enfin les protocoles de cryptographie que l'on utilise, si on n'a pas switché en PQC, ben en fait, on est vulnérable aujourd'hui à un ordinateur quantique. Donc c'est la seule façon de faire. Il y a pas, on peut augmenter la taille de la clé RSA ou Diffie-Hellman, etc., mais ça ne va pas augmenter la résistance si on a un ordinateur quantique.
Merci.
Une autre question? Oui.
Thank you for your insights that you shared in this talk. My question is not technical, but like from a general view, I want to know what is your POV like of the evolution of quantum security. Like people told us about the evolution of this field from like years from now, And like I guess there was a sentiment of hyping or overhyping about the topic. Like from your POV, actually now, like are there real solutions like based on quantum security that could help either red teamers or blue team in the world, like in the challenge we are facing daily? Like to debrief my question, do you think like quantum security has shifted from security research articles to real market? Thank you.
Yeah, indeed, the fact that we can break encryption, that's not the only outcome of quantum computing. We can also have tons of other applications, like the chemistry industry will be the first to benefit from it, for example. But us, as ethical hackers, as a weapon, that's maybe your question there. Yeah, Grover's algorithm, for example, could help us a bit for brute force or pre-image attack, for example. But here, it's just anywhere that we can use a parallelism using the quantum properties to have probability that we calculate together, that's where we could benefit from it. So, for example, AI, if I take another trendy topic, we can combine quantum and AI together and actually make AI more powerful when we have quantum computers at our disposal. Now, concretely, to build red team techniques and tools, that's not something that is straightforward because I do not see any obvious problem that we can solve today that we have, except encryption, actually. But research is ongoing, actually, and what you see here is that there is nothing obvious already. I would say, yeah, it's still possible that algorithm come out because everyone working on quantum computers, we could come out with new interesting algorithms. But as you can see, the algorithm makers actually are faster than the hardware. The Shor's algorithm was already designed in '94 and redesigned in between to reduce the number of qubits. So I do not have unless at the opposite of AI, there is no direct application as a weapon for ethical hackers, to answer your question.
Okay.
Hello. Here.
Oh.
Sorry. Sorry, I took note of my question. Yeah. It looked like most of your examples for usage of PQC were mostly private stuff, like Apple using it for their messages or Signal for end-to-end encryption, but it doesn't look like there's much public usage of PQC yet. Yet NIST is recommending that most keys using ECDSA, RSA, and so on be deprecated after 2030. Isn't that a little bit optimistic in a sense, since they're, for example, like TLS is still recommending using, or rather only using ECDSA at the moment, and it doesn't look like by 2030 it will be implemented for them? Is it something that's more like, hey, you should do it, or is there another bottleneck really preventing it from happening?
That's a good question here, because we need to do that on time. For example, change all the digital certificate, for example, that's a huge challenge. Yeah, I only took like a day-to-day example here, but if you take the US as an example, they invested recently $7 billion, I think, just to make the switch to classic asymmetric encryption to PQC, actually, for all the federal entities. In Europe, we're also asking ourselves the question, like, do we want to be led by other nations or whatever, like we did for AI, cloud, etc.? So, yeah, on the quantum level, the strategy is to invest in that because we have good researchers, we just need to activate them. So that's definitely a big challenge. If you take an example that is maybe TLS 1.3, for example, it is in the plan to implement PQC. This is not the case today, but it will be the case. So here for companies, that's really easy. They must take into account that TLS 1.2, of course, is outdated, but even more outdated because it doesn't have any PQC. But that's a huge challenge indeed. So for small companies, it's more about being aware of what do I have as cryptography asset management and what is including PQC or not. And if you do that from a resilience perspective, what if your conversation is stolen and read in 30 years? Will there be consequences for governments? Yes, I guess. For small companies, maybe less. But yes, first it's a work of awareness, and then it's going to cryptography asset management actually.
Thank you.
Merci beaucoup. Mesdames et messieurs, Robin, pardon.